Hello everybody, and welcome to the first beginner lecture of RUCP this semester. So today's topic will be Codeforces A and B problems. We'll get into what that means a little later, but just as like a note, the lecture is going to be fairly interactive, so we're going to pause frequently, see who comes up with what ideas on how, what problem solving strategy we should use for the next step. And because of that, it probably would be easiest to also have some paper and pencil and pens and whatever out as you write out scratch work, because some of these problems kind of involve pattern recognition, so some work like that is necessary for you guys to problem solve.
Oh no. Yeah, you're gonna have to back a lot of these problems because they're Codeforces A and B.
Sick. This is like a note on that. Okay. So, so A and B problems. That's good. So, in Codeforces, the A and B problems are naturally the first problems in the set. Since sets tend to be ordered in difficulty rating or in increasing difficulty, these problems are the place to start when you begin practicing problem solving in this setting. So the general approach to solving A and B problems is you're trying to basically make some observations on the problem statement, and from that you want to kind of figure out like a trick, like a fairly simple trick actually for most of these problems, on how you can get the solution usually very quickly. So it might seem intimidating at first, but we'll see that the problems oftentimes just boil down to something that's really fairly straightforward. So we'll go through that, and the best way to learn and gain an intuition for these kinds of problems is just to practice them a lot. So after all, it's pattern recognition, right? You have to build that up over lots and lots of problems. So so practicing is important, and that is what we will be pretty much doing in this first lecture. So let's also look at the general advice. So when you solve a problem, I think we mentioned this last week at the intro meeting, but there's two aspects to problem solving. The first is figuring out your algorithmic process that solves the problem, and then you want to implement it, which, so the first stage happens usually on paper, the second happens on the computer, right, as you code it up into whatever programming language you're using. And basically one of the main tips for solving these problems and not getting bogged down in debugging and all sorts of problems like that is to not rush into implementation too quick. So first you want a pretty solid idea on what exactly you're going to implement. So that's the common mistake done by many beginners. It's to start coding before even really solving the question. And so it's kind of a solve as you go strategy, and that, generally speaking, introduces bugs really easily, right? You don't have a clear direction, and because of that, you want to take things a little more slowly. You want to solve it on paper first, and sometimes take it back to the next level. Sometimes even think on how you would implement it yourself, figure out kind of like a general what the implementation would look like, and from that, try to think a little bit on how it would become easier to implement, given the different strategies. We'll see that a little later. And finally, right, they do give test cases, so you can kind of check your work on some of those. Sometimes the test cases are kind of large, so you want to kind of try smaller versions of the problem, smaller test cases, and look for patterns. And finally, there is the point that these problems, you kind of want to experiment with a lot of ideas, since you're trying to find observations that end up being useful, right, to actually figuring out or computing the final answer. So with that out of the way, let's get started. So our first problem here is called domino disaster. And basically, you're given a 2 by n grid, and you know that it's filled with dominoes. And these dominoes are labeled such that when they're horizontal, they are LR, so left and right, in their 2 squares. So dominoes are 2 by 1 blocks, just so that's clear. And the other kind, when we place it vertically, it will be labeled UD, up, down, or upside, downside, I guess. And basically, the problem is you're given the first row of this domino structure of the 2 by n grid, and you want to reconstruct the missing row. So I'll let people think on that. There's kind of an example. I guess if you cover the bottom row, you can kind of think about how the top row, or how the top row would yield the bottom row. So I'll let everyone think on that for a little. If anyone has any ideas, offer to share your thoughts. Yeah.
We just, if it's L or R, the other row is also going to be L or R, and if it's U, then the other one's going to be V, and if it's V, the other one's going to be U.
Yeah. So basically, that is the correct approach. So you might notice, or probably notice eventually, that a lot of the dominoes are actually fixed once you are given the first row. So whenever you're given an up square, you know for sure that there has to be a corresponding down square or D square at the bottom in the second row at that position. And then for the left and right dominoes, you can just notice that once you fix the top 2 squares, there's no way you can fill the bottom 2 squares without eventually somehow overlapping it. So basically, you can just kind of copy the LR onto the second row. So does that make sense? Are there any questions? No? Okay. So moving on to the next problem. Sorry, not to the next problem. Here's the code. So there are some notes about this code that are kind of important to know. So this is in C++. We assume that you know how to code in something like that, so either C++, Python, or Java. And there are only 2 real things that maybe require me to go over real quickly. So the first is LL. What does LL mean? So a trick in most of our templates or most of our code structures, which we will go into more detail in the next lecture, is that you can basically set it up so that instead of having to type out long, you can just type out LL, and that's then the same for long. So it's just less to type, it's faster to type, it's more convenient, and it's just recommended by us. And so just replace every L, you can kind of think of it just as int in Java, or Python, just it's a type, I guess. And finally, the second thing that I wanted to note here is cin. So that is how you read in data, and cout is how you output data, or make output in C++. So so basically, when you write cin, then you make those arrows, and those arrows you can think of point in the direction that the data is flowing. So when you read in data, right, it's going from the console, or the input, where that's going, into the variables. So in this second line there, we have cin to n, so we're reading in n, which is an integer, or long now. And at the last line there, we have cout, which is, again, it's the direction that the data is flowing. It's going from our variable result, or right, into the console, so, or the output. And that is how you remember the arrows. I think apart from that, those are the only main differences. Otherwise, it should be fairly readable if you're familiar with code. And maybe one more thing is that you can chain your inputs together. So you could have defined your string before reading in n, and then done cin the arrows n, and then before writing a semicolon, done also the arrows s, and that would have read in n and then s. So maybe it's more intuitive that way, or in this language compared to others. And yeah, then the code structure is pretty much what we just described just before it goes through the entire input. So are there any questions on anything here? Yes.
Is Endo just a new one?
Yeah, so end L, for now, you can just think of as a new line. Technically, it does some other things, which matters for only a small number of problems. But yeah, for now, just think of it as a new line. All right, so next problem. Our next problem is odd divisor. So if we are given an x less than or equal to 10 to the 18, we want to determine if it has an odd divisor bigger than 1. And so this is a kind of just a yes or no question. You want to print out yes or no appropriately. We have some example test cases there. And one thing to note, I guess, about the 10 to the 18 part of this is that 10 to the 18 is large relative to the time limit that you're given. So the general rule of thumb is that you're given 1 second usually, and that means 10 to the 8th operations times a small constant, but roughly 10 to the 8th, on the order of 10 to the 8th operations is what you're allowed to work with. So for this big of a number, you're not going to be able to say brute force all 10 to 18 possibilities because that would take long. So
Can we give suggestions?
Yeah. So in the room, I'm just gonna probably ask the people in the room first, since it's easier to like all loud. Okay. Okay. All right.
Oh yeah, there's a bunch of people.
First, does anyone have any ideas on how they would approach this problem? Yeah.
So you just keep on dividing by 2. If you reach 1, then it does not have an odd divisor. If you reach an odd number, it's not 1. It has an odd divisor.
Okay. So we have a candidate solution. Yeah.
Go along with this, I think, on, probably where he has no.
All right. That's all right. That is a or no. Yeah.
Can the divisor be the number itself?
It's on, yeah.
Yes. It just has to be bigger than 1. So unless it's on. Yeah. So now we have some suggestions for the solution, and now we will look at the actual solution, which is pretty much what was said. So the key observation to this problem is if you were to look at some random smaller numbers, try to find any patterns, you would see that powers of 2 will satisfy this condition that all of its divisors are even if they're greater than 1. And then you can also reason that out, right? If the number has any prime divisors, right, that are not 2, well, then we can just use the prime divisor, right, since it will be odd. So with that, we know that this number must be a power of 2 in order for there to be no solution. So in order for the answer to be no, right, if there's no odd factor. On the other hand, we then want to, it's just the opposite for yes. And so as noted on the slide, 10 to the 18 is small enough to the point where we can just generate all powers of 2 less than it, and then just manually check each one to the number. The suggestion is also valid, where we can basically repeatedly divide until we get an odd number. If that number that we have at the end is odd, and that's when we terminate. So we're eventually going to get 1 or some other odd. If it's 1, we know it's a power of 2 since we were just dividing by 2 the whole time. If it's not 1, well, then we just found our odd factor right there. Okay, so I think that's all for this one, apart from the implementation. So the implementation here is the latter because it is quicker to implement. As you can see, it's just a simple or a single while loop on a single line. And if you just, okay, so there is a little trick on the second, on the output line there. It is basically a ternary operator, right? And it's pretty much, you can just think of it as asking if x is 1, it'll do the first option. If it's not, it'll do the second option. So it's kind of just an if-else, no, yeah, an if-else statement just like squeezed into a single line. Any questions on the implementation? Okay. So moving on to, before we get to the next problem, it is going to involve maybe a new topic to some of you, and that is the bitwise XOR operator. So I think, or yeah, if you've taken 111 or have got it before, you're probably aware of the other more standard bitwise operators like and, or, not, I guess, but we're just dealing with operators that take in two inputs. So and is, as you would expect, if both conditions are true, then it gives true. Or is if at least one is true, it will give true. And now here is XOR. So XOR is short for exclusive OR thing. And that basically means if the two numbers, so it's basically, when you learn about OR, people always say it's if X is true, Y is true, or both are true. They kind of specify that. And XOR is when you kind of ignore that last one. It's exclusive. It's when you have one has to be true, and that would then mean the other one would also have to be false in order for your XOR statement to evaluate to true. And in bitwise terms, that you just convert trues into ones and falses into zeros. And so because of that, we get this truth table. And the operator, in I think all languages that are relevant, is the caret sign. So not exponents, it's XOR. And I think that's, okay, and I guess the final note there, in other words, is basically just, you can also think of it as if the two digits are different, then we have a true evaluation. Otherwise, if they're the same, then it's false. So some properties of XOR, which are pretty useful in the problem solving process, is in our first one, we have if we XOR a number with itself, we'll get 0. That's because all of the bits will line up, right? So that you're always XORing something with itself in each binary place value. And because that we get 0. Then we have A XOR 0 is A for any A. So that comes from the fact that, you can just, yeah, basically it's similar to the first one, but you can just check manually that 1 XOR 0 is 1, 0 XOR 0 is 0. So that it's reasonable that 0 is the XOR identity. It doesn't change the number. The next one is that XOR is commutative. That again follows from the truth table directly. And the last one is associativity. So it doesn't matter in which order you take your XOR. So this structure is quite useful in most problems that involve XOR. Actually, it's necessary for them. And finally on the side, there's that little thing there that if A XOR B is C, then we can basically XOR, or XORing more of the sides, gives you A and B in that way in those cases. But again, but you can just get that from the original identities, more specifically commutativity and associativity and the first one. So let's see problems that this is more concrete. So here is our first XOR problem, XOR sequence. And basically you can think of it as kind of a Fibonacci type definite or sequence for given the first two elements. We define the next as the XOR of the previous two. And then we want to compute the nth term of the sequence. And the interesting part is in constant time. So we can't actually go through ourselves and manually compute every single value in between. So this is a problem that's, yeah, so there's like a pattern that you might notice if you read the hint, or if you follow the hint, right? So yeah, paper would be useful here. Write it out later. If anyone has an idea, volunteer.
It just repeats, like we see it in the cycle.
All right, so we have an observation, and that observation is going to be useful once we do this. All right, brute force, right? All right, we have the definition of the next term, just from the definition. All right, now we apply the recurrence relation, or the formula, onto the next term. And here we see that we now have AX or B, X or B. So using the rules, right, we can kind of just think of it as, one big XOR string, AX or B, X or B, from associativity. Then B, X or B, cancels, and then we're just left with A. And that comes from the structure of XOR itself. Then with the next one, we get a kind of a similar result, right? Where we're now XORing A with the previous term at S2 as with AX or B, and then same logic as before, it cancels again. We're back to B, and this is, we reach the cycle, right? So our cycle has a length 3, repeats every 3 terms. And again, you can also kind of reason this out from the structure or the properties of XOR directly, although in practice, it's probably easier just to notice it by brute forcing it yourself for the first couple times. So, all right. So for implementation purposes, we basically, in the beginning, since the cycle occurs in has a length of 3, we can kind of discard any multiple of 3 from our n, because it will just repeat. That's that's just how we would use mod in this case, the modulo operator there. And the implementation, because of that, becomes quite simple or short. Also, we use the different end line variation here. So instead of actually typing out end L's, but end line, here we just did the character directly. So both work. It might be, generally speaking, it's safer to use this one, but at this point, it really doesn't matter which one you prefer. So again, any questions? Okay, so the double arrows are just part of the syntax for input and output. So in this, so you put it in between everything that you're kind of outputting. So in this case, you kind of read it as output A and then a new line. And to remember the directions of the arrows, you think of the direction in which you're sending the data. So for output, it's going from the variable name, right, the variable, to the console, right? Whereas for input, it would be the reverse. It would be going from the console, cin, into the variable. So the variable name would come second. Yes, it would. Yeah, that's just a syntax thing. And the thing I said is just like a mnemonic, I guess. It's like a way to remember it. But yeah, that's like probably the most substantial thing for now. That is different from my physics part. Yeah. All right. So moving on, we have a second XOR problem. Personally, I don't like this one too much, but we have it. So given some integer n, we want to compute the XOR from 0 up until n. And again, it's going to be maybe similar to the last one, where we want to just try out the first terms and see if there's a pattern. So I'll let people try to find the pattern now, I guess. Yeah. Yes. So like when we're XORing, right? Yeah, we are XORing the binary representations. I guess when I introduced it, I was introducing it in like the context of Booleans, but when we're XORing numbers, yeah, we are XORing it. Yeah, place by place if you were to write it in binary. So, sorry if that wasn't clear. And it's like if you do the same with like or and, right? It would have the same. But it's like the bitwise operation itself. So, um, which
So if you were doing this in a contest,
Yeah.
you would just loop through it and see what's going on.
That is
Would that-
that is a
Would that be a strategy?
I just
So,
put the first one.
yeah, so in a contest, right, you don't actually have to like manually compute things too much. After all, you do have a computer in front of you. So an option would be to brute force the first say 100 terms, right? See if try to conclude the pattern from there. So actually, I'm just gonna do that to make people's lives easier.
Anyone?
I like to suggest that.
0, 1, 2,
Oh,
I just calculated the 0, 1, 1, 1, 0, 1, it's 1, 1, 0, 0, 1, 1.
It is more long the same as 1, 1, 1.
Okay, I said it all.
Oh, you said a binary. You say it like normal.
That would be 1, 3, 1. 7. 1, 3, 1, 7.
You forgot some.
I'm gonna show it.
I forgot to do it.
Alright.
You forgot some.
So for convenience, there are some terms for you.
I think we said it, but like you just dropped it.
Yeah, so I guess one thing to like remember is that these numbers you can also they are in binary, right? Since you are doing the operations on them in binary. But like remember that they're also decimal numbers too. So sometimes, right, it's easier to think about numbers just in that lens. So here's the pattern.
Well, as Jim said, it's mod 4, so it repeats every 4 It repeats every 4 numbers, but there's still one more to be done.
So we can maybe pick that up from the zeros, which seem to return or pop up, you know.
Anyone? Yeah.
I would, yeah.
Looks like every fourth one.
That's true.
That is true.
That's true.
Every first of the 4 is in the full 4.
That is also
Okay.
true.
Okay.
Okay.
That's true.
What about the second? What about the second one? What is the second? Yeah.
The one,
What about the one?
3 plus in the full 4. I think it's always an increase in the full 4.
Plus 4. So the first one is 0 plus it adds 4. The second one is always 1. The third one starts as 3, adds 4 every time, and the last one is 0.
So let's see. So we can no, this is the group. So we have the first few terms. Now here is the general formula. Now in a contest, I guess you could guess it. It's not. Or okay, you want to guess it, and then there's the question of, is your guess correct? So you could just submit it directly, right? See if it's right that way. If you want to be a little more safe about it, there is kind of a like reasoning you can kind of put together, again, because of the structure of XOR. Um, kind of because the bits
You wanna,
would.
this one would definitely be better on the whiteboard. I mean, blackboard.
I don't want to explain it.
Okay,
It's-
yeah.
it's
I
like-
explained that.
This isn't a particularly big problem. So, yeah, it's just like a pattern. And okay, so one approach to kind of convincing yourself that this is the correct pattern is to approach it by induction. So you would basically say, okay, we have these first three sets or three, cycles. Now, can you convince yourself that the next cycle will behave in the same way? So if we end it at a 0, right, then the next one, or either if we end at a 0 and the next one's 4K, then if we end at a 0 and we XOR it with a number that's divided by 4, you can see with the indices, it would line up that way. We would then get another multiple of 4. Then with the 1, you would just take adjacent, a multiple of 4, and then a number 1 greater than a multiple of 4. And can then kind of line up the bits and see that they would pretty much cancel, except for the little bit that doesn't. And then that would leave you the 1, then the 4K and 1 would XOR for a 4K plus 3. Again, here's where you're kind of lining up the bits yourself and figuring out what it would look like from there. But yeah, this is kind of like a reasoning that you construct from by looking behind, right? So the step to actually figuring out this formula is fundamentally just a guess. It's if you wanted to really convince yourself, I guess, or before you start making guesses, you could look at more terms, which then yes, simulation would be your friend in that situation. So moving on. Never mind, not moving on. We have the code. The code is pretty much what I said. Now, it is multiples of 4, but it's also increasing multiples of 4. And since the cycle is 4 long, you might have noticed that back here, the multiples of 4, when we say it's 4K, it's actually, well, yeah, it is the index itself. So from that, we get the simpler, yeah, we got relatively simple this casework on that. So I think that's all for the implementation that we need to cover from this. So we have a construction problem. So in this problem, you are given an integer x, and you want to find two other integers, a and b, that are smaller than or equal to x and bigger than or equal to 1. And you want to find them such that b divides a, so a is divisible by b. That's the first condition you want. The second condition is that the product is bigger than x. And the third is that a divided by b is smaller than x. And that is going to be actual division, not like int division the way C++ would normally do.
That doesn't matter because I have to.
That's a good point. So yeah, it doesn't even matter. Never mind. Yeah, and then if they exist, you want to report on that. If they don't exist, report on that. So let people think about this for a little bit. And yeah, the hint. Again, A and B problems. It's usually just a couple observations at most, and you don't want to overthink it too much. There's no algorithms per se or fancy data structures or anything. It's just clever little tricks. And there are some examples on the book. Oh, actually, something about the examples. So when you have a problem that is constructive like this, where you want to, construct some A and B that satisfies whatever, the sample, or like when they give you the example output, you might notice that it's not very helpful, sometimes because they're gonna, intentionally not reveal the like intended like algorithmic um, approach towards like where you can just like reverse engineer from that. So unfortunately, the examples just illustrate the conditions, not the actual algorithm. Yes.
In your example,
Yes.
so we'll always apply it.
If you do that.
Except for
Okay. So.
You know,
Yeah, a little louder.
you can do that. You don't have to just pick x minus 1. It's also including x. So you can also do
you can also
So,
less than or
to
yeah, that's it.
yeah. So I think we heard the answer. So we will cover it now in a little more detail. So we have casework here. So the general approach, before I'm going to do the edge case last. The general approach is to just say A is equal to B is equal to X. If A is equal to B, well, we don't have to worry about the A divides B condition anymore because that's always going to divide to 1. Now, we wanted, if we look back, we want A divided by B to be smaller than X. So we already want to like make a mental note that X is equal to 1 is probably an edge case. It's probably going to be some case that we have to handle manually. So if we choose A equals B equals X, right, then A over B is handled. We see that X times X will be greater than X. That's AB. Now, X squared is only greater than X if X is bigger than 1. So again, 1 is probably an edge case. And finally, A is divisible by B. Oh, I think I handled that. Okay, yeah, A is by B, A is by B, yeah. And so we can see that for 2, right, we can choose 2 and 2. 2 times 2 is 4. 2 divided by 2 is 1. That works. Any number bigger than 2 would work. So now the problem is X is 1. So if I'm going to go back to the problem one more time. If we say X is 1, right, then we see that 1 is less than or equal to A, which is less than or equal to X, which is 1. Well, that means that we can only make A equal 1, and same with B. But then we have a problem where 1 times 1 is not bigger than 1. So this is the only situation in which we would have no solution. Did everyone follow that? Okay. Great. So any questions? Here's the implementation. It's okay. I think we actually did do that special case. Oops. But it's pretty simple. Yeah, maybe problem. So yeah, this is assuming X is not 1. If X was 1, you would just have one if statement saying if X is 1, no solution. Otherwise, bad. So yeah. No questions? Our next problem is grid type problem. So we are given a 2x2 grid, 2-dimensional grid with n rows and m columns. That is the standard dimension variable names which they would give you. And we want to color each of the cells either white or black. And so this is another constructive problem. We're trying to generate a grid with the given dimensions that will satisfy this condition. And the condition is, if we were to count the number of white cells that are bordering a black cell, and then designate that as W, then we were to count the number of black cells touching a white cell, designate that as B. We want our final grid to basically have one more of these black cells. So B has to be one bigger than W. So I'll let people kind of try it on paper, try a couple of things, see what works, see what doesn't work. There's a example, but again, the examples on constructive problems tend to be misleading because they don't want you to reverse engineer the convenient solution. And a note is that there are no restrictions on how many white or black cells you can put. You just want, you know, any grid that would satisfy that.
Is there guaranteed to be a solution to?
There is guaranteed to be a solution because, yeah, we can just guarantee that directly. Yeah. And I guess maybe one tiny thing is n and m are bigger than 2, are bigger than or equal to 2. So for each of them, which maybe is what guarantees the solution. I mean, you probably like the point is not. So, yeah. Yeah. Oh yeah, touching is defined as just cardinal direction. So it's like an edge. It's not corners. Sorry. That could. Yeah.
You have the solution just other way around because B equals
Yeah. So that's very nice. So we have right. We have the solution. So basically we want to exploit. I don't know. Make a very convenient looking grid, and that grid would be to just put a white square in the top left corner and then make everything else black. So note how having the blacks adjacent to each other a lot like that will actually, make them not count to the total for B. And by having one white, you can only have one W. So because of that, we kind of just innately naturally simplified the problem to something that's a lot easier to think about if we use this approach. And then you'll see from kind of just the diagram that it would work. What?
Oh, okay.
Actually?
Yes.
Okay. Well, I just.
All right. And then
one more problem.
you can just like make the rows and column numbers a lot bigger. You can see that they would all be black. Nothing would change. That was the. Right. Moving on. Nope, not moving on. Again, implementation. It's just some for loops, some if-else statements. There's nothing too fancy. You'll notice that that's kind of how competitive programming works. It's a bunch of just like basic building blocks that you just use over and over and over. So, all right, moving on. We have an LCM problem here, number theory. So we are given L and R, and we want to. So another constructive problem. So the examples might not be very helpful. But given L and R, we want to find two integers x and y such that they are in between L and R inclusive. And then we want their LCM to also be in between L and R. X and Y can't be equal to each other. So one is strictly less than the other. Just, without loss of generality, just randomly just say it's X. And then LCM is the typical definition, in math. It is the least common multiple. I guess at the bottom, there is a side note. Please don't use that in this problem. But the LCM, so the formula at the bottom might be more intuitive if you think about it as x times y equals the LCM of xy times the GCD of xy. And that makes sense when you think about it. If you think of the numbers in terms of their prime factorizations. So when you construct an LCM from two numbers from their prime factorizations, you're basically taking the primes, right? And then you're lining them up and correspondingly. And then you're taking the larger exponent of the two, since that number will be the number that will guarantee to have the numbers divided into it. GCD, similar thing, but now you're taking the minimum. And then when you take the LCM times the GCD, you're basically taking for each prime the larger exponent one times the minimum or the smaller exponent one, putting it all together, and you just get the product, as you would normally, without caring about which one's which. So, I'll let everyone think about this for a little bit. If anyone has any observation, volunteer to share. And yeah, I guess what I noticed in some of the previous problems, you're trying to kind of like exploit the problem. You're trying to like really find like sometimes a silly solution. Sometimes.
It kind of feels like the last problem, in a way.
Yeah. A little bit.
So you find the primes between L and R, and then you construct the LCM first, and then you just like split it into X and Y.
Okay. Now I will say to that, let's say L and R, they can be huge, 10 to the 18.
Okay, so you just start with L and just until you find like 2 primes.
The problem with that is that in order to find primes, you need to check up to the square root, right? So that's going to be, there are tricks, but I don't think they're fast enough. 10 to the 18. I saw that. Yeah.
Just set X and Y.
One tiny thing there is that X and Y have to be different. X is less than Y. But good instinct. Yeah.
There are cases where this can't be possible.
There.
L and R, given L and R. L is 14, L and R is 15. We want 14.
Yeah.
I
There are some
got
tricks.
it.
So it has to be the lowest thing.
Take L plus L plus 1, L and L plus 1. And you just multiply them, that's the LCM.
That is an approach.
It might not be.
An example would be like 6 and 18, because 6 times 7 would be 42. So you'd have to like check more than that.
There's still a couple more
There are.
But you guys are doing like right. It's not like a simple approach example.
There are cases.
Wait, no, but 6 and 18 is not possible.
Yeah.
It's not possible.
Yeah, so that is the intended solution. So,
Okay.
the key observation is that if you were to say make a number and then with another distinct number consider its LCM, well, since they're different numbers, the LCM will have to be greater than the smaller number, naturally. So, because of that, the smallest, we're kind of trying to think about how we can force it to be the smallest, the best, the optimal, the tiniest LCM possible. And that is if we just say x and then we take 2 times x, but that's the next multiple. It's the easiest one we can get, since any other would imply we can get 2x also. Now, we would, to kind of like try to squeeze it in, we would take x equals L and then y equals 2L, and we'll see if that will guarantee us a solution, but it's not an actual solution, right? Because we have to check if it's actually still in the range. So we do that by confirming that it's still less than R for both of them. And that is the, so just a note. So I think on the Google Meet call, it might end abruptly.
All right.
If that's gonna happen, okay, we're just gonna.
Wait, there's another.
There's 2 or 3 problems left. So if that happens, just like a quick like conclusion remark is
Can I just like open?
actually never mind. Okay, never mind. Well, okay, never mind. Scratch that. If the meeting ends abruptly, we'll probably spend a minute getting it back up.
Yeah.
So please be aware of that. Anyways, to the next problem. So this next problem is about strings. Strings, by definition, are pretty much sequences of letters ordered sequences of letters. So they all have position, and we can have repeats. We can have all that kind of stuff. And then we define a subsequence to be kind of like a subarray, if you're aware of that. If you're not, then a subsequence of a string is basically some of the characters if we were to delete some of the other characters. So it has to be in the same order that it appears in the string. For example, if we have AXY BCK, then ABC is a valid subsequence. And the next definition is a period. So a period is going to be, kind of in a hand wavy way. It's going to be what you expect. So here's the more numerical definition. Basically, if a string has a period k, where if for every character with index I, it is the same as the character in index I plus k. So that's the length of the period. If they're equal, and that's true for every index, then or every index such that I plus k is still in the string, then we say that it has a period k. And then the example there is, if we have a bunch of zeros, period is 1, because that. The other one is basically 0, 1, 1 repeating itself. A thing to note, actually no. So that is periodic, as you would. So the problem is binary period. Basically, if we're given a string of size n, and the string s will have only zeros and ones, I believe, we want to construct another string such that the first condition is that the given string is a subsequence of this string that we constructed. The second one is that the string we're constructing is at most twice as long as the original. And the third is that we are minimizing the period or the possible period of t, which it has to be periodic. So, it will have to be periodic. And then I will let people think on this.
Among Us?
Among Us? Okay.
That's very cool.
You don't have to admit me anymore.
This is me.
How many people are in the room right now?
There's a few. But yeah, well, we're getting this thing set up, so work on it. No, seriously. Adam, can you?
You unmuted.
I'm unmuted.
Okay. Hi, Adam. What's your question?
Set that up again.
Sorry. Someone has a question. We're waiting
It doesn't. You don't have to minimize the length. You don't have to minimize.
Okay. Okay, so that is a key part of the problem. You're not trying to minimize the length, but you are trying to minimize the period. So, yes.
So if the string is only 1, 0, only zeros, you would just basically repeat it.
Yep, okay.
If it starts with the 1 and has zeros, you would use the string 1, 0, 1, 0. And if it starts with 0 and has 1, you would use the string 0, 0.
Okay, I think we heard the correct approach. So we will now vote. Yeah. Pretty much. That's close enough. Okay, so
I don't think it is.
yeah, so we first have a little bit of casework, just a little bit. The first case, right, as suggested by the hint, we look at, let's say the period's 1. So that's only true if the entire string is all zeros or all ones. If that's true, we just spit out the string again. No need to change it, right? Since it's already periodic. Now, if it isn't, the observation is that if we consider the string 0, 1, 0, 1, 0, 1, and so on, or I guess 1, 0. Yeah, 1, 0 also works. Yeah. So basically, so we know that now since 1 has failed, since we're doing that, looking at other cases, we now are going to try to make it do 2. And our claim is that this is always going to work. And the approach is to basically use all 2n slots, which we have no minimization requirement on. And then when we print out all these 0, 1s, you can notice that our original string of size n will occur as a subsequence, right? All we do is we just, say in the first 2, we say, okay, the first from the original string will correspond to whichever one is in the first 2. The second corresponds to whatever's in the next 2. Since it's only 0s and 1s, we're going to hit everything, or we're guaranteed to hit everything like that. And yeah, the problem is solved. Are there any questions on this approach?
Yeah, I think so.
Yeah. Oh yeah, sorry. Yeah. Oh, sorry, I said yeah. Okay. A little bit. And we're gonna move on. So now we're gonna do the code again. Yeah, it's just what you would expect. Again, nothing too fancy. For loops of statements. That's pretty much all we have to do here. Oh, maybe another thing. The way you access characters in C++ strings is in the same way you would access elements in an array. So you just think of strings as character arrays and work from there. I think that's the only new thing to note here. So I got maybe a tiny thing. When you're printing out here the 0, 1, you're not note how we're not putting a new line after it. So it's just gonna like pick up where it left off from before. So that is a little detail, I guess. There's nothing else to discuss, I think. Okay, next, even picture. We have an infinite grid of squares, and we want to color some of the cells gray. So another constructed problem. Okay, and we want to satisfy this condition, or conditions. And the first one is no gray cell will have an odd number of gray neighbors. So no 1 gray neighbor, no 3 gray neighbors. And we are looking at, again, neighbors, cardinal directions, edge connections, no diagonals. And next we have the n, or we're going to be given some n, and we want to guarantee n of the cells to have 4 gray neighbors around it. And the final condition is we want all gray cells to be connected by cardinal directional paths. So no diagonal connections, and that is the problem. So there is a hint, a reasonable place to start. Productive, and I'll let people think on this for a little bit. Again, you might want to draw this one out. Doing it in your head, I wouldn't recommend it. Yeah.
And more than n gray cells have 4 gray neighbors.
No, I don't think so. I think no. But you can have more than n gray cells. Kind of obvious. Because there's got to be at the core.
Oh, this is cardinal directions only
Yes,
again.
this is cardinal directions, no diagonals. Yeah.
Wait, so it has to be like exactly 1 gray cell.
Or 3. Must be odd. Wait, sorry. Can't be odd.
Yeah, I'm saying like what's the hint saying?
Oh, the hint saying is that let's say you fix n as 1. What would the solution look on that? Usually, a hint like this is implying an inductive way of thinking. So it's like once you have 1, okay, now how can I get 2? Well, now that I have 2, how can I get 3? Is there a pattern? Oh yeah. Oh, okay. Right. So it's that, but setting n equal to 1. So you have the infinite grid, and you want exactly one gray cell to have 4 gray neighbors, and then each gray cell will have an odd number of gray neighbors.
Wait, which color is gray? Sorry.
Okay, so yeah, this is it's dark gray is gray.
I saw the big plus sign. Right?
So I think that's one approach. It's one approach. The problem is implementation. Actually, not.
Oh, it's the infinite grid, so you can just.
It isn't. I think.
How would
Wait.
you-
Oh, never mind.
How
Never
would you
mind.
solve for odd
Never mind.
factors?
The problem with the big plus sign is that as you make the like length of your plus, like the top, longer, then you're gonna have gray squares at the top that only have one. You know, a 3 gray around it, 1 non-gray, and that's not
Wait, do you
allowed.
want to like draw your thing?
Uh,
How like big is the plus sign? Like,
so it's just like just by 1, like width of 1.
oh,
So
Yeah, it's the same problem.
Yeah.
It's the same problem. As it gets like longer, you're gonna see little basically you're gonna see on like the edges. You're gonna have these cells that are surrounded on if you're looking, here's the plus sign. You're looking on this side, the one that's here, above to the left or my left, and then to the bottom you're gonna have rays since it's like a big plus sign. But then to the right, this is above the center. It's gonna have 3 adjacent rays and
So
1.
those-
You don't want that.
You're going to have something on the side that has
Yeah.
3 neighbors that are gray. You
Yeah.
can't have odd number of gray neighbors.
I don't think.
Do you want to draw it out?
No, it's just
Yeah, well, they're all.
it's just
All right. Sure. Was
so
it?
this one.
Yeah. Yeah.
three.
So how many neighbors is this one?
As you extend it out, you start getting.
It's just
You
Oh,
can't-
right.
you
Yeah,
can't-
it's pretty close though. Yeah.
Well, you have no way out.
That's n equals 1. Yeah.
The grid is.
Yeah.
You can't color it.
So, for any where they're like that, you know? And for n equals 2, you're gonna have 3 vector structures.
This is supposed to be for n equals 3.
They work.
This is n equals 4.
Oh yeah, this is n equals.
No, more. It's
It's
yeah. So you want to be able to handle any n. But the first one was definitely correct.
Yeah.
And you want to think on.
That it's
how you
close.
can
It's,
use
it's
this.
kind
Yeah,
of like the expanding idea.
on the right track.
but-
On the right track.
Can you draw your n equals 3?
So just draw on the board.
Yeah, draw on the board. Draw on the board. If anyone else has a thing, draw on the board.
Sure.
Okay, yeah, draw on the board. Yeah. So, oh, that's 4. That's crazy. So let's have like a base structure where that's the base structure, and then for n, you're gonna have it's n plus 1 base structures connected diagonally. So let's like
Somewhere
consider
for
n
that.
equals 1. Then you can have it like this. And then you just repeat it into 2. Same thing, but you just add on.
Yeah.
So I'll just do one more control like that.
All right, I think we have a. I don't know if there's
They have
progress
a
there.
solution.
Oh, we also
They
have a solution here. Okay. Yeah. So. Okay. Very nice.
Yeah.
job.
That one was close, but you expanded the wrong diagonal.
Yeah, so, yeah, so, yeah, okay. So here are some options. One of them is probably easier than the other to think about, but this is how you would approach the picture. So yeah, we have one there. I think we have one there. We have one on the right track also, but yeah, this is sort of just like a visual argument, I guess, just convince yourself. Yeah.
I'm with you. I actually have a much simpler solution.
Really?
Yeah, go ahead. Yeah.
No.
No, draw the board.
You want, I can give you. This is a by M plus T.
Oh, the corners don't.
And
the
also
corners have
3 by M plus.
But if you have a rectangle with corners, well, I mean,
Corners have
sides.
two.
The sides.
The
Yeah,
sides.
the sides can be-
Yeah.
That has one non-gray.
Wait.
Has one non-gray. No odd like gray neighbor counts.
Like, look at the sides. Okay, look at it. Yeah.
The sides have-
Close to it. Like, if that wasn't a condition. We got close. All right. So yeah, I think the one on the left is probably more intuitive. You just kind of just keep stretching it or building on it, and yeah. There's no way we have an implementation. Okay, good. All right. Okay. So moving on to the last. I think this is the last problem. Troublesome. So basically, you're given an array of size n. So that's array A. It's going to have a bunch of numbers. You're trying to sort them. And you're given a second array named B, and it's a bunch of zeros and ones. And basically, the rule is you can swap any two elements in A as long as the elements, so their corresponding B. Okay, never mind. I shouldn't explain this. You can swap the elements in two indices as long as the indices in B correspond to different numbers. Yeah. So so in the example, you have 3, 1, 2, 0. That's not a good example. 3, 1, 2. The second example, 0, 1, 0. This would mean that you can swap 3 and 1 since B has a 0 at the 3 and a 1 at the 1. One thing to note is that as you swap them, B stays the same. You don't swap B as well. You only swap A. And the question is, are you able to sort the array given these rules? Okay. What do you think of that? Yeah.
You're allowed to do
As many as you want. Yeah. Don't worry about. Yeah. So you can do it however much you want. You're not trying to minimize anything or anything crazy like that, but you are trying to determine if it's possible. Yeah.
Possible if the elements maybe the elements B were
Not necessarily, but you're on the right track. Yeah.
Okay, we have a claim. Why do you think that?
You're allowed to do it.
Yep. All right. So we have a solution. So I'm gonna move on or to the solution and cut out. All right. So we have the first case, an edge case, and that is basically if B is the one value throughout, it means that we can't do any swaps, right? So we can immediately check if we're stuck, right? If A is sorted already. That is the first. First case. Next case, we have at least one pair of indices such that the values in B are different. And as it turns out, we can. This actually gives us a lot of power in rearranging, and that's because we kind of in the way where how we would swap variables normally. We can kind of treat one index as a temporary kind of placeholder, and then swap things Yeah, and now we can on demand swap any two indices in A or elements in A, and just like that, we can sort the array. A little more concretely, if we're trying to swap I and J in this example, so we have two cases. First case is Bi and Bj are not the same. If that's the case, well, we can swap them directly. We're done. However, it might be a little more challenging, right, when they're the same, because now we can swap them directly. So by our construction at the beginning with the two cases, we know that there's at least one element k that will differ from whatever value of b we have at I and j, since they're the same. So because of that, we can do those three swaps. So basically, kind of treating k as kind of like a temporary one, and because of that, we can swap I and j while leaving k alone in the end. And just like that, we can swap any two indices anywhere in the array, as long as we have one differing pair. So, if that makes sense. Any questions?
I have a question. So what if you have a B array where it's like half zeros and then half ones in that order, and then there's like the A is just in a random order? Can you still do this?
Well, the whole point is that once you have the I and J like this, so so this works for any array.
Or there's at least one difference in B.
Yeah, because and then like intuitively, right? If you think about the opposite, right? If there is no difference, well then you're stuck, right? Immediately. And I think that is that all? Why is it?
This is an implementation.
There's an implementation. Yeah, whatever. It's just what you expect.
What you would expect.
Yeah. There's not too much to say about it. It's just, again, lots of little pieces used in the appropriate order. And thank you for coming. All of this material will be on Discord and everything. The next lecture topic will be data structures, so basic data structures, built-in data structures, and the C++ standard library. We'll do that in the next lecture, which in 2 weeks. That will basically explain the actual code that we were, presenting here, instead of just doing problems a little more abstractly. And but a little more pressingly, we have the mentor contest next week, same time, same place, and everything. Now, this would be a good opportunity to have pretty much one of us or someone who's more experienced in competitive programming, guide you through like a set of problems, and basically guide you through the problem-solving part, the common implementation mistakes, the template, whatever. And also, there'll be pretty much no pressure. And that is all for today. So,